Hello, hello. Welcome to lesson 10B. We're still talking about the chi-squared test or hypothesis test, but we're going to look at two different types of tests in today's lesson. So last time we talked about the goodness of fit test. This time we're talking about the test of independence and the test of homogeneity. So let's recap. We have three different types of tests, as I mentioned last time. So one of them is the goodness of fit test, which is really when we're dealing with one sample for one variable. A chi-squared test of homogeneity and a chi-squared test of independence are going to look pretty similar in terms of how the data is given to us. The little bit of difference has to do with how many samples I have and how many variables I have. So a chi-squared test of homogeneity, you can think of homogeneity basically means sameness. We're testing for are these two samples or three samples or whatever the same. All right, so this is when we have two or more samples of data and you're looking at like a single variable across those two or three samples, and you want to know, do we have evidence that those two or three samples or populations are different? The chi-square test of independence has one sample, but multiple variables. And we're really testing for, are these multiple variables independent or dependent of each other? So let's look at it a little bit more closely. So the big question, obviously, is how do I know if it's a test of homogeneity or a test of independence? Because they're going to look very similar in the way the data is given to you. So firstly, know that the math part of it, the calculations, is essentially the same. It's pretty much the same test. The only real change comes in the wording of your hypothesis statements and in your conclusion. So just be aware of that. There's really not a huge difference between them, so it's not going to be a major thing. But a test of homogeneity is when we have separate samples are taken, and we're really comparing the two or three or whatever samples to each other. And a good clue is in the way the question is asked. If they ask, is there evidence of a difference between blah, 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 blah. It's a good example. For a test of independence, we have one sample. So if they talk about a sample is taken, and we're looking for some level of dependence or association between variables, that's a test of independence. And oftentimes the question that you're asked is something like, is there evidence of an association between? So let me give you some actual examples. In this one, we have a table. It looks like this. It gives us like different things that people did after they graduated high school. And then we have years, 1980 and 2000. So this would be like, a sample of high school graduates was taken in 1980, and they were asked about their post-high school plans. And another sample was taken in 2000, and they were asked the same question: is there evidence of a difference in post-high school plans between 1980 and 2000? Okay, so based on the wording and based on what we have, that would be a test of homogeneity, right? We have two separate samples because they were taken in different years. So we have two different samples of high school students. And then we are asking about evidence of a difference in those post-high school plans for the two different years. On the other hand, here is another table. It looks the same. That's why I'm saying it's sometimes hard to tell. It's the same type of two-way table. But what we have here is we have gender along one side, and then we have what their favorite TV show is on the top side. Or what their favorite thing to watch on TV is. And the question that might be asked here is, do we have evidence that there's an association between your gender and the type of TV show you like to watch? So in that case, we kind of have one sample about which we collected two different variables, right? We collected information on the variable of gender, and then we collected information on type of TV watched, right? So this would be a test of independence. We're testing for an association between variables, but we really just have one sample. So that's a couple of examples of the difference between the two types of tests. Again, the math part of it, the calculations are the exact same. What really changes is what we write as our hypothesis statements and then how we interpret or conclude our results. So let's talk about hypothesis statements for a chi-square test of. So for homogeneity, again, the whole goal is looking for sameness. Do we have evidence that there is a difference between these samples in terms of this variable or are they the same? So my null, remember, null hypothesis for any test is that things stay the same, that nothing's different, nothing changes, everything's chill. So our proportions of whatever we're dealing with, whatever variable we have, are the same for all groups. That would be our null. Our alternate would be the proportions of whatever variable are different for all of the groups or for some of the groups. A test of independence, the essence there is we are testing for association. Does one variable affect the other in some way? So our null hypothesis is that there's no effect, no change, no difference. One variable has nothing to do with the other. They're completely chill. So that would be basically the null, that there is no association between the two variables or that they are independent. Right? Because that's saying basically that one doesn't affect the other. And that's what our null always is. Nothing changes, nothing's affected, everything's cool. Our alternate would be that there is an association or relationship between the two variables. In other words, that the two variables are dependent, that one does affect the other. They do have some kind of impact. Whatever happens with one variable is changing what happens on the other, right? If you remember that our null is always same, things don't change, everything's chill, and our alternate is always something happened, something's different, something's being affected. These are guides to help you know what the hypotheses should look like, but we always are going to write your hypothesis statements in context. So include variable names, include group names, make sure you're being specific. So let's look at an example. A survey organization conducted telephone interviews in December 2008 in which 127 randomly selected adults in the US responded to the following question: at the present time, do you think television commercials are an effective way to promote a new product? In January 2018, another sample of 131 adults responded to the same question. The data is given in the table. Is there evidence of a difference in opinion on television commercials? So here is the table. Right, so we have the answer absolutely yes, somewhat yes, depends on the product, and absolutely no. So we have 4 different opinion or answer categories. And then we have the 2 different years. So first thing to decide, because before we write our hypothesis statements, we need to know how to write them. We need to know what type of test this actually is. So this would be a chi-squared test of homogeneity. And that is because we technically have 2 different samples, one in 2008, one in 2018, but also we are dealing with where we're looking for a difference of opinion. So because of those 2 things, we're looking for a difference in opinions between 2 samples, and our samples were clearly taken separately in different years. That would be a test of homogeneity. So when I write my hypothesis statements, remember our null is that the proportions of whatever we're measuring are the same for the 2 samples. So I would say something like the true proportions for each opinion category are the same for 2008 and 2018. And then my alternate would be that they are different, right? That the true proportions of each opinion category are different. Remember, with a chi-squared test, we are not ever saying less or greater, because obviously the less or greater is going to change on each category. We're just saying different. The other thing I wanted to point out and remind you, our hypothesis statements are always about the population. So be careful not to mention the specific sample. Don't say the proportions in the sample are the same for 2008 and 2018, right? We're talking about the population. We're always using our sample to estimate or make a guess of what's true for the population. So our hypotheses are always about the population. So the next step would be to do our math. Actually, it would be to check conditions, but we need to do math before we check conditions. Our conditions, by the way, are essentially the same as for our chi-squared goodness of fit test. So in order to do the conditions, one of the conditions was that our expected counts need to be greater than or equal to 5. How do we find expected counts? With a goodness of fit test, we were given those kind of hypothesized proportions that we could use to find the expected counts, and we don't have that here. So how do we figure out what to expect within each category? So I'm going to give you a little formula. It looks like this. For each cell in the table, the way you would find its expected count, so this top left one, is we would do the row total, so add up all these numbers and find that row total, times the column total, So add these two and get the column total, and then divide by the overall grand total for everybody. Now, I'm not going to go into this on here. If you're curious, you can ask me about it. But where this comes from is it's the idea that if there was no relationship between year and opinion, then we would expect the proportions for absolutely yes to be the same for 2008, for 2018, and overall. So where this is coming from is kind of looking at if the overall proportion of absolutely yes was the same as the 2008 proportion for absolutely yes, this is what it would have to be. So that's where it comes from. Again, I can kind of show that math for anyone who's interested, but for now, just know that that's how we find the expected count. So, for example, for this top left one, I would add together 28 plus 48 plus 31 plus 20 to get the row total. I'm going to do the math in a second. All right, did a little bit of math. Make sure I'm going. Okay, so I did a little bit of math here. So I added up the row total, 28 plus 48 plus 31 plus 20, which is 127. I added up the column total for that first column, so 28 plus 20, which is 48. And then I went ahead and added all the numbers together to get the overall grand total of people, which is 258. So if I find for that top left column, the expected count would be the row total, 127, times the column total, 48, divided by the overall grand total of 258. When I do that, I get an expected count of 23.6279, etc. So if I were to do that, and then I would go on and do that separately for the next one. So for the top row, second column, I would do that row total times that column total divided by the overall total. So if I do that for each one, these are the expected counts that I get. You may be wondering, am I actually going to have to do all of those maths for each one? Not really, because when we do the chi-square test in our calculator, it'll actually figure out the expected counts for you. But because this is part of our conditions, it is important that we actually write the numbers down, and I'll explain that in a minute. The other thing that we would need to know, especially if we were going to do this test by hand and use the chi-squared table and all of that stuff, is what degrees of freedom is. So again, with a goodness of fit test, it was categories minus 1, but now with this type of test, we have kind of two different groups of categories, right? We have categories for opinion, and now we have categories for year. So the way that we find our degrees of freedom is by doing the number of rows minus 1, so 2 minus 1 is 1, times the number of columns minus 1. So there's 4 columns, 4 minus 1 is 3. So 1 times 3 is 3. The other quick way to do degrees of freedom is if you cover up a row, like I usually do this with my hand. You cover up a row and then cover up a column. However many cells are left is your degrees of freedom. Again, the calculator will figure this out for us, but it's helpful to know where it comes from, especially on multiple choice questions. So now we're ready to kind of do the test as a whole. I wrote chi-square test of homogeneity up here. Remember that this is what gets you out of having to write out the formula by hand. So it's always a good idea. We can talk about our conditions. So our first condition is, do we have random samples? And because we are technically dealing with multiple samples, that's what part of what makes it a test of homogeneity, is that we have multiple samples. We also need to kind of say that they are independent samples. So looking at my example, it says that the December 2008 sample was randomly selected, and in 2018 it says another random sample. So we're given 2 samples. We can assume they are separate or independent of each other since they were taken in separate years and it says separate. So we were given 2 separate samples of adults in 2008 and 2018. And then our second condition is that expected counts need to be greater than or equal to 5, which we just showed that they are. So all expected counts are at least 5, so it's appropriate for us to do this problem, to use a chi-squared distribution. So now we can do the math. We can do the math, find our chi-squared value, find our p-value, and then write our conclusion. It's the last step. So let's go ahead and go to our calculator, and I'm actually going to go back to where the table was because I'll need that. So in my calculator, where I'm going to put this information, because obviously I don't want to have to do the math on this by hand. So I'm going to go to my calculator. I'm going to go to the matrix menu. So because my information has multiple rows and columns, the best way for the calculator to get that kind of all in one place is in the matrix. Even lists, like using stat edit, that's technically putting it in different lists. So we're going to do second matrix. Oops, push the wrong button. Try that again. Second matrix, which is the x-1 button. Then we're going to go to edit, and we're going to edit matrix A. And this is where we're going to put our observed data from the actual sample. This is a 2x4. Rows come first, then columns. But just remember, right, what it should look like on your calculator should mimic what it looks like on the page. So that's how you know that you have the right dimensions. And then I'm just going to type those in, right? So 28, 48. When you push enter on your calculator, it's going from left to right. So that's the easiest way to put the data in there. So I'm just typing. Okay. Make sure to push enter after your last cell so that it actually gets entered. And then once we have that matrix in our calculator, this is really important, second quit. Matrix menu is weird on your calculator. If you don't second quit anything you try to do after that, it's going to try to do it like in the matrix. You have to get out of the matrix. So once we've done that, we are ready to do our chi-square test. That's it. That's all we have to do. Because when the calculator does the chi-square test, it figures out the expected counts for itself. So we don't actually have to type those in. So that's different. For a goodness of fit test, we do have to type in the expected count. For a test of homogeneity or independence, the calculator figures it out for us. It also figures out the degrees of freedom. So I'm ready to go do my chi-square test. So I'm going to go to Stat, Tests, scroll to the bottom, and we want the regular chi-squared test. GOF is for goodness of fit. The irregular one is for the other two types. So chi-squared test, observed is in A. The calculator is going to put the expected counts in matrix B for us. We don't have to put them there. And then calculate or draw. I like calculate. And then it gives us a chi-squared value and a p-value, and it tells us what our degrees of freedom is, which is super handy. So we did conditions. Now we know our chi-squared value was 11.35. P-value is 0.00995. I kept going because it kept rounding up, which is weird. And then we do the same thing we always have, which is compare our p-value to a level of significance. Did this problem give us a... No, it did not. It did not give us a level of significance, so we can use 0.05. So since 0.00995 is less than 0.05, we reject the null. We have evidence of our alternate, which basically said that there's a difference in opinion about TV commercials between 2008 and 2018, that the proportions of each type of opinion are different for 2008 and 2018. So that is how we do our test of homogeneity. Again, really what makes it this type of test is in the way that we word that we're talking about a difference as opposed to talking about independence. So that is our test of homogeneity. Let's move on and do another example. It'll give us some practice with the math because the math is the same. And it'll also give us a look at the other type of test. So an AP statistics student is obsessed with Harry Potter, as they should be. She decides to take a survey of 100 random, actually I think it's 200. I changed this later. McNeil students and ask them their favorite core subject, as well as what Hogwarts house they would be sorted into. The following table shows the data she collected. Does the data give strong evidence that the favorite core subject is associated with Hogwarts house? So here's our data. Here are clues about what types of test it is. She took a survey and just asked them two different questions. So we really have a sample with multiple variables. And then the question is asking about association. So because of those two clues, we can say that it's a test of independence. I am going to take a second and pause and go back and fix the sample size because it's not 100. I was right. It was 200. All right. So null and alternate, when it's a test of independence, our hypothesis statements are about independence or dependence. So our null hypothesis, remember, is that everything's cool, nothing's changed, one thing doesn't affect the other. So my null here is that favorite course subject and Hogwarts house are not associated. They are independent, right? Because one doesn't affect the other. There's no change, no effect, no difference, no weirdness. Everything's boring. And then our alternate is what we think might be true or what we're testing for, which is that favorite core subject and Hogwarts house are associated, that one does affect the other, or that they are dependent. So null is that they're independent, no relationship, nothing happens. Alternate is that they are dependent, there is a relationship, one does affect the other. Next would be to do our conditions, which means we do have to know what our expected counts are. We were told that it is a random sample. We can have our first condition. We don't need to say that they're separate or independent samples because they're not. That's part of what makes it a test of independence, which sounds weird. When it's a test of independence, we don't have to check that the samples are independent. I know. It's two different types of independence. Anyways, so we're going to go to our calculator and do the same thing we did before. This time, I'm just going to have the calculator do the expected counts instead of having to do them myself, or like I showed you before. Just as a side note, multiple choice questions do like to throw things in where you have to know how to find expected counts by hand. That's why I show you what it is. So I'm going to go to second matrix. I already have a matrix in there, but I'm just going to type over the numbers in matrix A. If you wanted to completely clear it out, the only quick way I know of doing that is just to 2 + 7, 1, 2, right? Just to clear out the whole calculator. But you can type over data that's already there if you want to. So this one's also a 2x4. Not every problem we do like this will be a 2x4 matrix, but both of these examples have been. So I am typing in my observed values. Ta-da, they're all in there. Everything's happy. Second quit. Okay. And then I'm going to go ahead and run my tests. So I'm going to run the test, just regular chi-squared test, and then it'll give me all the information. And then once I've done that, I'll come back to this later, but I wanted to show you once I've done that test, if I go back and look at matrix B, these are my expected counts. So the calculator figures it out for us and puts those values in matrix B. Okay. Again, on a free response question, you do need to somewhere type or write what those expected counts are. You can't say expected counts are greater than 5 if you haven't shown what the expected counts are. So I like to do that just in the original table they gave me. I put them in parentheses. You can make a new table and just type them out. However you want to do that, but you do have to actually show what the expected counts are. They are all greater than 5, so yay. The degrees of freedom would still be 3 because these are the same dimensions as before. But remember, rows -1 times columns -1. Okay. Then we're going to do some calculations. Apparently I forgot to set the transition things on this, so there are all the answers. My conditions, I was given a random sample. So we're going to assume that sample is representative, but we were given a random sample of all McNeil students. And all expected counts are greater than or equal to 5 is true. Again, make sure you show your expected counts on your paper. If I go back to, and I disappeared it, but if I just go back and redo the chi-squared test, again, there is my chi-squared value, 6.32. There is my p-value, 0.097, and then they give me degrees of freedom again. And then again, we'll assume alpha is 0.05. since 0.0971, our p-value is greater than alpha, we fail to reject the null. We do not have evidence of our alternate, which is that there's an association between core subject and Hogwarts House for McNeil students. Again, make sure if you're not going to show the formula for chi-squared that you write the name of the test. So write chi-squared test of independence if you don't want to have to write the formula. Otherwise, you have to write out that whole formula. It's the same formula for chi-squared that we used for the goodness of fit test, but you would have to write it all out if you didn't write the name of the test. All right, so that is it for this lesson. We'll talk in class next time.